Hi, I'm Z, and I'm a student at the Australian National University studying the Bachelor of Philosophy Science. Today we'll be focusing on dice and probability. So the equipment that we'll need include 2 dice, a piece of paper to record our result on, and a pencil. To start off with, we would like to start with the question, if we roll a single dice, which number would you expect to see the most often? When you're thinking about an answer to this question, we'll need to use the idea of sample space, which is all of the outcomes that can occur from this experiment. In this case, we've got the numbers 1 to 6 on the dice. So to record the results of our experiment, we're going to need a table. This table you can download from the website, and up the top we have the numbers 1 to 6. These numbers match with the number of dots that are here on the dice. For example, over here, this one, we have a number 1, all the way up to 6 over here. So now we're ready to start the experiment. I'm going to roll the dice and observe here that we have the number 3. So I'm going to add a tally under the number 3 in the table. And let's continue this. So this time another 3. So let's add another one under 3. And we're going to repeat this 10 times to start with. Now that we have done the experiment 10 times, we're going to calculate the experimental probability for each number. In order to calculate the experimental probability, we're going to use the formula that the experimental probability is equal to the number of times that the event has occurred divided by the total number of times that you have done the experiment for. So from the table, we can see that the number 1 happened once and we did 10 trials in total. So we're going to note that the probability of 1 happening is equal to 1 over 10. Similarly for number 2 also happened once and we did 10 trials in total, so we got an experimental probability of 1 on 10 as well. For 3, however, we observed 3 twice when we rolled the dice, so the probability of 3 happening would then be 2 over 10. And we're going to calculate the probabilities for the other numbers similarly. So now we're going to do the experiment 10 more times and see if we observe any changes in the experimental probabilities. Okay, this time we're going to do our calculation a little bit differently. We're going to use the combined result from this first experiment that we did, along with this experiment that we've just completed. So altogether, now we've done 20 trials, and we're going to count the number of tallies under both of those rows. So for the number 1, we've got it happening once in our first experiment, and then another 2 times when we just did the experiment again. So altogether, we should have that the probability of 1 occurring is 3 out of 20. For the number 2, once again, we have 1, 2, 3. We saw the number 2 3 times, and we did the experiment 20 times in total. For the number 3, we've got 1, 2, 3, 4, and once again, we did the experiment 20 times in total. And we're going to do the same calculations for the numbers 4, 5, and 6 similarly. So we're now going to repeat the experiment once again, rolling the dice 10 more times and record our results in the table and repeat the calculations similar to what we've done before. And this time you would have done 30 trials, 40 trials, 50 trials, and finally 60 trials. 2, 5, 1, 4. So now for the third column, we've done the experiment 30 times, and let's count the number of times that we observed 1. So we have 1, 2, 3, 4, 5. We get 5 over 30. For number 2, we also observed the number 2 5 times, and we've done 30 trials in total. And we're going to continue until we've filled up the whole table. So now you're going to repeat this experiment another few times until you have filled up the table, which ideally should be 60 trials in total. At the end of your 60 trials, ideally the probabilities that you have calculated should be close to 1 over 6 for all of the numbers. So for this experiment, we shouldn't expect to see any numbers occur more frequently than the other. If they do, it may only be a marginal difference. So this is where our idea of theoretical probability comes in. Theoretical probability refers to the probability that we get in theory. So the number of desirable events out of the total sample space that we were talking about at the very beginning. So for the dice, our sample space is made up of the numbers 1 to 6, hence our denominator for this probability would be 6, and each number occur on the dice once. So we have that the probability of each number occurring should be roughly 1 to 6 when we do this experiment. Okay, now we're going to take this experiment one step further, and we are going to use 2 dice for the next part. You will be using this table, which once again can be downloaded from the website. So for this one, we're going to once again try and predict which number we will see the most often. But now that we're using 2 dice, the number that we record is no longer the number that's on any one of the dice, but the sum of the numbers. For example, if I roll the dice, I observe a 4 on the blue dice and a 4 on the red dice. So the number that we're going to record down will be 8. As another example, this time I've got 6 on the red dice and 3 on the blue, so the number that we'll record down will be 9. So this time we have a larger sample space, and in order to help us work out what our sample space will be, this is where this table comes in helpful. So along the top, we've got numbers 1 to 6 for the red die, and down the column, we've got the numbers 1 to 6 for the blue die. The way we want to use this table is we simply want to add up the numbers that we have here. So for this cell, we've got 1 plus 1, so giving us 2. 1 plus 2 giving us 3, 1 plus 3 giving us 4, and we'll just repeat this process for the entire table. Cool. So as you can see from the completed table, our sample space for this new experiment will be all numbers from 2 all the way up to 12. Okay, now we are going to repeat our experiment similar to part 1, and we're going to roll the dice 10 times and record the number of outcomes that we see. Now that we have completed the sample space table, we're now going to use a third table, which also you can download from our website, that lists all of our possible outcomes at the top. So in the case of a 2, that would indicate when we have a 1 and a 1 on both of our dices. For a 3, we would have a 1 and a 2, etc. until we get up to 12, which would be both dice showing 6s. So let us now roll our dice and see what numbers we get. So we have a 1 and a 1, so they make 2. Let's add a tally under 2. Rolling them again, we get a 1 and a 2, making 3. So 1 tally under 3. This time we get a 4 and a 6, making 10. So 1 tally under 10. And we're going to repeat this 10 times, similar to the last experiment. And now we're going to calculate the experimental probability for each of those numbers occurring using the formula that we've seen in the previous part. So for the number 2, we've got the number 2 occurring once, and we did 10 trials in total. So we would note down 1 over 10. For the number 3, similarly, we noted down that it occurred once during our experiment, and we did 10 trials in total, so it has a probability of 1 on 10. Some of the more interesting numbers that we got, we observed the number 7 twice, in which case we would write that the probability of us having 7 would be 2 over 10. And for 8, we didn't observe it at all when we rolled the dice, so we would note down that the probability for an 8 for that particular experiment was 0 out of 10. And we would complete the rest of the table similarly using the same formulas. Okay, now that we've finished the calculations for the first 10 throws of our dice, let's do it 10 more times and record our results under the second row. Now that we've completed the second 10 throws, let's calculate the probabilities again. And once again, we've now done 20 trials in total, and we want to count the number of times that the number showed up under both the first and the second row in our table. So for the number 2, we have observed it twice in our 20 throws, so we would note down 2 over 20 for our probability. For the number 3, we've got 1, so we will note down 1 over 20 for the number 3. And we're going to complete the rest of that row similarly. Now that we've completed the second row of our table, you're just going to continue rolling the dice until you've finished the 60 trials, similar to last time. So now that you've completed all 60 throws, which number occurred the most often? Were your guesses correct? Now, in order for us to find the theoretical probability for each of our numbers from 2 to 12 occurring, we're going to jump back to this table that we've completed before we started the experiment number 2 with the 2 dice. So we can see that in this table, we have 36 grids from 2 ranging down to 12. So the total number of elements in our sample space would then be 36. So for the denominators of our theoretical probability, we're going to have 36. And we see that out of the 36 grids that we've recorded, only one of them has a 2. So the theoretical probability for the number 2 happening would then just be 1 over 36. For number 3, however, we see the number 3 twice, once over here and once again here. So we have a probability of 2 over 36. For 4, we see 4 3 times, here, here, and here. So we will note down 3 over 36. And we're going to repeat this process for all of our numbers up to 12. Cool. So after doing all of these calculations, we see that the number 7 has a theoretical probability of 6 over 36, which is the greatest out of all of our numbers from 2 to 12. So if you repeat this experiment an infinite number of times, then you would expect to see the number 7 occurring the most often. So this concludes our experiment with the dice. Hopefully with these 2 activities, you were able to understand a little bit more about sample space, theoretical probability, and experimental probability. And lastly, I just have one extra challenging question for you, and let's see if you can figure it out. So imagine you're in a game show where there are 3 doors. Behind one of the doors is a car, and behind the other 2 is nothing. You pick a door, and the host will reveal to you a door that is not the one that you've chosen, and behind which there is nothing. After the host reveals that one door, you will get a choice, whether you want to switch to the other unopened door, or stick with the door that you have originally chosen. So probabilistically speaking, should you switch doors? So in order to solve this problem, think about the sample space for this event and the theoretical probability for each of those events happening. Work out the probability that you will win the car if you make the switch, and the probability that you'll win the car if you don't make the switch, and see whether you or not you should make that switch. So thank you for watching this video. Hopefully you've learned something about probability from this, and hopefully I shall see you again soon.